Okay, here is week 20, part 2. So we've got some previously released AP questions. And this situation is there's a compressed spring up here with a mass, and you can imagine you push the mass in for some distance. We don't know how much distance. And then you release it, and the spring is going to push on the mass, and by the time it gets here, all of the, I'll zoom in a little bit. By the time it gets here, all the elastic potential energy, so the spring potential energy, has been turned into kinetic energy. So we would know some sort of velocity, and it's going to slide off frictionlessly. And then this situation here is like what we studied with parabolic motion, right? It's a trajectory, a projectile, and the distance that it falls is going to determine how long it's in the air, and the horizontal velocity and how long it's in the air is going to determine how far it goes. So we have those values. So the first couple questions are sort of a review of this projectile motion, where question number 1 says, calculate the time elapsed from the instant block A leaves the table to the instant it strikes the floor, meaning how long does it take to fall this distance? So in that case, if we take a look, so how long does it take to fall 0.8 meters? Remember, the horizontal velocity doesn't affect falling, so the fact that it's moving to the side does not affect how long it takes to fall. This is our good old formula of the month, where the displacement of final position, I put a negative 0.8 with the initial position of 0, initial velocity of 0. This is the initial velocity in the vertical direction. Yes, it is 0 as it begins to fall. And then we plug and chug and get 0.4 seconds for the time it takes to fall. Seems like a reasonable value. This is about the height of one of our desks. Part 2, or B, excuse me, then asks for the horizontal velocity. So for projectile motion, horizontal velocity is constant. So when calculating how far something goes, we're just using distance equals velocity times time. A lot of students, we had a question on our final where it was a projectile motion, and the question was asking how far does it go. A lot of people were using this formula for that. That's not correct because it's not accelerating. I mean, you could use that formula and plug in 0 for this, and then you just get distance equals velocity times time. Anyway, so here we go. We know it went this far, and we know it took that long for it to go that far, so we can solve and get a horizontal velocity of 3 meters per second. Okay, so that was a review of our projectile motion stuff. Part C then relates to the spring and springiness and whatever. Calculate the distance x the spring was compressed. So, based on the fact that this thing is now going, is that a 3 meters per second? Let's just make sure. Don't look at that answer. Alright. So, based on the fact that this thing is going 3 meters per second as it leaves the table, how much was it compressed? So this is where you're going to relate the spring potential energy to the kinetic energy of the mass once it leaves the spring. So spring potential energy 1/2 kx squared, and that's going to equal 1/2 mv squared. Spring potential energy here equals kinetic energy there, and what do we say? Oh yeah. Whoa, hey, uh-oh. Things are getting weird. So we say 1/2 kx squared equals 1/2 mv squared, and we get that the displacement, the amount the spring was compressed, is 0.24 meters. Cool. Alright, so I think that's it for this first page, but let's read this question here, because this part I cut and pasted not so well. This applies to question D and E. It says block B, also of a mass 4 kilograms, is now placed at the edge of the table. So this guy, same situation, only there's another mass right here, and this thing is going to fly into it, and they lock together and then do this. Well, that's what we assume. So The spring is again compressed to distance x and released. As it nears the end of the table, instantaneously collides with and sticks to, so is that elastic or inelastic collision? Good question. To block B, and then they follow a trajectory shown and strike the floor. Okay, so how does that affect, alright, so these two stick together and are going to follow some trajectory that we assume is going to be less. So conservation momentum says that the momentum of this is the same as the momentum of the system, and the momentum of the system after will be the same as the momentum before. So you could do mv plus mv for both blocks before and say that's equal to mv plus mv for both blocks after. But you might just think about it and say, well, because these things have the same mass, and this is going 3 meters per second, after they collide, they're going to be going half that, or 1.5 meters per second. And you would be perfectly correct. So their speed, let's see, what does this actually ask us? Let's focus here. D, calculate D as if x is equal to, okay, so how far do they go? And we assume they're not going to go as far as the 1, and that's a good assumption. So, hey, my answers are lost. Ah! Oh well. Just wing it. So, I'll write it all out. So, calculate D. So, what do we know? We know that it went a distance of 1.2 meters, and the horizontal velocity was 1.5 meters per second. Oh no, this is what we're looking for. Sorry. We know that it took 0.4 seconds to fall. Alright, so if it takes 0.4 seconds to fall and it's going this fast to the side, we can simply multiply them. Again, horizontal motion, the horizontal velocity stays the same, and times 0.4, and let's see, so I think that's going to be 0.6 meters. It sounds good, because that's half, half of the 1.2 that was the one mass by itself, so that makes sense. Now, part E, so with these questions, you really have to read them carefully. There's a lot of detail, so let's see what this says. Consider the system consisting of the spring, blocks, and table. Spring, blocks, table. How does the total mechanical energy, so total mechanical energy, meaning potential and kinetic, E2 of the system just before the blocks leave the table, compare to the total mechanical energy E1, we're calling it, of the system just before block A is released. So E2 is after the collision, so they collide just before they get launched, and E1 we're saying is just like this. So here there's lots of potential energy, and we know that's turned into kinetic energy, but something happens during that collision. So because they stick together, that is inelastic, and what we know is that, whoa, inelastic, what we know is that in an inelastic collision, momentum is conserved, but kinetic energy is not, meaning energy is lost due to sound or heating up of the molecules or compression or whatever. So because some energy is lost, we're going to say that the energy after is less than the energy before. So how does total mechanical energy E2 of the system just before the blocks leave the table? So E2 is after the collision, and E1 is before the collision, so E2 is less than E1. And that's because energy is lost in an inelastic collision. Good work.